Differentiating exponential functions. E is approximately 2.718 and so on. But as you can see here, this number goes on forever. Like pi, it's an irrational number. Consider the graph of y equals 2 to the x. So 2 to the x looks like this. We can see it crosses the axis here. So the y-intercept is at 1. And that should be clear because, of course, 2 to the 0 is 1. It has an asymptote as the negative x-axis. We can draw the gradient function of this curve. This is possible without knowing the differential, or we could use software, as I've done here. And this is the gradient function of y equals 2 to the x. Note how it's the same shape, but the gradient function curve is always below the original curve. So look at the intercept that I pointed out earlier. We can do the same sort of thing with y equals 3 to the x. So here is y equals 3 to the x, and we've also got its gradient function. This suggests, because the gradient function with 3 to the x is just above, that there's a number between 2 and 3 where the gradient function lies exactly on top. And you could probably guess which number that is. So the green one here is y equals e to the x. And yes, the gradient function lies exactly on top. And in fact, I've plotted it here, and you can see the green curve poking through the dashed yellow one. It follows that if y is equal to e to the x, then the gradient function, which we know is dy dx, is also e to the x. So this function differentiates to itself. Of course, this can be established by other means, such as limiting chord and formal proof. It can also be established that if y is equal to e to the kx, where k is a constant, then dy dx is ke to the kx. This is something called the chain rule. So as mentioned, it's an application of the chain rule, but the chain rule is something that you're going to learn about later.